Yeah, this is day 4 of 50 days of tutelage, and we are having math class again. So, this is our second math class. We are taking indices and surds in this class. Indices is actually there are a set of rules that we need to follow whenever we're dealing with indices problem. And these rules, the more you use them, the better you are familiar with them. So, the rules are not really your major problem. It is how you apply them that you need to watch out for. And there are basic rules that we need to follow. So I'll quickly list some of those rules out right now. The first one is whenever you have a common base. And then let me quickly describe what we have when we have indical equations. What does it really look like? So if you have an expression of the form a raised to the power of b. Now this a is the base and this b is the index of b. So a is the base and b is the index. So whenever you are dealing with any operation of this form, then you are dealing with indical problem. And there are a set of rules that you need to follow. You need to know how we deal with these things. One of the major problems that I've seen students face so far, or one of the common misconception and mistake that I've seen students make so far, is imagine you are given something like a raised to power b plus, k raised to power c. Students will just assume that, oh, the base, they go pari passu, so you can say a plus k, and then you add the power as well, and you say b plus c. This is very, very wrong. So to avoid mistakes like this, I'm going to give you the list of the rules that you need to always follow whenever you're dealing with problems in indices. So let's get down to it. So the first one is the law of common base, which deals with multiplication. If you have a base a raised to power m, and you're multiplying with another thing in base a raised to power n, then you can easily write this as a single base and add the power. Now, this same thing goes for division as well. A raised to power m divided by a raised to power n, then this is going to be a raised to power m minus n. Note that the converse is not true. What do I mean by that? It doesn't mean that whenever you have a raised to power m plus a raised to power n, then you say, oh, pick one a and multiply m raised to power n, or you say a raised to power m plus n. It is not going to be equal to any of these. So this is true from left to right, and you cannot just remix it and do it like this thing on the right. So the left hand side is the one that is true in all of this. So let's go again. Now, what if you have a raised to the power of m, and this is also raised to the power of n? It can actually interchange because this thing can be written as a raised to the power of n raised to the power of m, and it can be written as a raised to the power m times n. Note that this a raised to the power m raised to the power n is not the same thing as a raised to the power m raised to the power n. What this means is you would have to find the m raised to the power n before you now find a raised to the power whatever the result is. So let me give an example. If you have, let's say, 2 raised to the power 2, then raised to the power 3, this ultimately means 2, it's the same thing as 2 raised to the power 3 raised to the power 2, which is the same thing as 2 raised to the power 6. However, if you have 2 raised to the power 2, then raised to the power 3, it means that you have to do 2 raised to the power 3 first, which is 8. 2 times 2 times 2, that's 8. Then you now find 2 raised to the power 8. So you can see that they are not the same. So take note of that difference between the two rules. So we have the first rule here, the second one, and we have the third one here. So let's go again. There's another rule that says that a number raised to the power of a negative power. Whenever a number is raised to a negative power, then it can easily be written as 1 over a raised to power n. So basically what that is doing is that you forget about the negative sign and you just take the inverse. So if I say 2 to the negative 5, so if you forget about the negative sign, that will be 2 raised to the power 5. So just find the inverse of 2 raised to the power 5. That will be 1 over 2 raised to the power 5. And that's what the rule is saying. So take note of that. That's another rule. Now let's go to another one. There's another one that says a raised to the power 0 equals 1. But however, Take note, a itself cannot be equal to 0 in this case. This is true if a is not equal to what? 0. So any number raised to power 0 is 1 as long as that number itself is not equal to 0. So, and these are the major rules of indices. Of course, there are other ones, and those other ones actually they are predicated on some of these other rules as well. Another one is 0 raised to power any number is going to be equal to 0, provided that that number is not equal to 0 itself. Yeah, there are quite a lot of them, but this is not really what matters. What matters is for you to be able to apply it. For you to be able to apply it. So this is what I'm going to be doing. I'm going to be taking as many questions as possible. So after the class, you can always send your question to me via my email. I'm going to drop that for you. So I'm going to take an example now. I'm going to show you how we actually solve indices problem. Indices problem are not really, the problem with indices problem are not really indices, but proper knowledge of algebra, how to factorize, how to manipulate, how to write numbers as product of prime factors. And you know, in the previous math class, I had taught you about number system. So let's take an example and then we move to surds. Now we have 3 raised to power 2n plus 1, then minus 4 raised to power 2n minus 1. Then this is divided by 2 raised to power n plus 1 minus 2 raised to power n. So this is what we have. We need to simplify this, get it into the lowest term. So there are so many ways we can go about this. And the first thing that is coming to my mind is for us to actually apply this first rule that we have here. Yeah, this first rule that we have here, such that when the power are we are going to be using the second rule as well. When you are adding the power, it means that you can separate it as a base and multiply it. So what do I mean by that? We can go from right to left now. A raised to power n plus n, we get something like a raised to power n plus n. So if you notice 2 raised to power n plus 1, that implies that we can write it as 3, then this will be 2 raised to power n multiplied by 2 raised to power 1. So what I've done is that I've separated this now. Instead of the common base now to be isolated in one place, I have de-isolated the common base so that they are separated. It's just a reverse of the rule. Minus, I can do the same thing for this. This will be 2 raised to power n. Now, here's something I can do. This can be divided by 2 raised to power 1. But I want to show you something quickly here. If I have 2 raised to power n divided by 2 raised to power 1, it means 2 raised to power n over 2 raised to power 1. It means 2 raised to power n multiplied by 1 over 2 raised to power 1. And that means this is 2 raised to power n multiplied by. So if you remember, if you have the inverse of a number raised to a power, it can be written as that power raised to the negative power. So instead of 2 raised to power n here, I can make this one 2 raised to power negative 1. So permit me to change this, because I just want to have multiplication signs only. Permit me to change this to multiply by 2 raised to power negative 1. So I believe that makes sense. Now divided by, this also is splitted, 2 raised to power n times 2 raised to power 1 minus 2 raised to power n. So what you notice here is that 2 raised to power n is common at the numerator. It's also common at the denominator. So therefore, it can be factored out. So this whole expression becomes 2 raised to power n. So what do we have left here? We have 3 outside multiplied by 2 raised to power 1 is 2. So we have 2 inside. Minus, we have 4 outside. And what will be left here is 2 raised to power negative 1, which is the same thing as 1 over 2 actually. So we're done with the numerator. For the denominator, when 2 raised to power n comes out, you have what is left there, 2 raised to power 1, which is 2, minus, when 2 raised to power n comes out here, it's like this is being multiplied with 1. So you have 2 minus 1 down here. And now, that implies that 2 raised to power n can cancel out. And up here, you're going to have 3 times 2 is 6. Then 4 times 1 over 2, that's going to be 2. Then 2 minus 1 is 1. So therefore, at the end of the day, the entire simplification of this is equal to 4. So for indices, you just need to practice as many problems as possible. The more you practice problem, the better you get at solving problem with it. So we're going to be solving tons of problem on this. I'm going to be giving you a lot of worksheets to work on. So let's move to sort quickly as we proceed into this class. Now, sorting expressions. Generally, whenever we have anything that involves square roots, so of course we have cube roots, we have fourth root, we have 10th root, and so on like that. But for now, we're going to be dealing with, let me start with nth root. Now, if you have the nth root of a number, this can be written in the indices form as a raised to power 1 over n. But if you also have it as nth root of a, and this a is being raised to a power as well, you can also write this thing as a raised to power m over n. Take note of this. So you can see it in indices form. Now, there's another mistake that students usually make, and that is about this n. There is difference between n root a and nth root of a. So you can see that this nth root of a is written just within the sign, and this other n is written outside the sign. This one indicates that the a here is a square root, and this one indicates that you have what we call nth root. So if I say what is the square root of 8, it's different from, okay, let's do it like this. If I say what is the third root of 64, is different from when I say 3 root 64. So third root of 64 is equal to 4. That is, if you multiply 4 3 times, 4 times 4 is 16, then 16 times 4 is going to give you 64. However, this means 3 multiplied by, what's the square root of 64? 8. And that will be equal to what? 24. So get the difference between these two now. Now, so quickly, let's look at the rules that we need to follow when we're dealing with sorting expressions. The first thing you need to know is that if you have square root of m multiplied by square root of n, note these guys are of the same root, square root, square root. Then you can say this will be square root of mn. If you have square root of m divided by square root of n, then you can put them together as square root of m over n, provided that n is not equal to what? 0. Now, this would work if they have the same root. If it was, let's say, 8th root of m multiplied by bth root of n, this guy, you will not be able to blend them together as something like, let's say, ab, then you have mn. You won't be able to do them this manner. So take note of that. So I'm going to be using square roots, but just know that whatever I use as square root, it also satisfies for upper root as well, like higher root. Now that we're done with division, so you know that square root of m plus square root of n is not equal to square root of m plus n. And neither is square root of m minus square root of n, neither is it equal to square root of m minus n. This is not going to be so. So take note of that. Take note of that. Now, we have some other things that we need to. So when we are doing addition and when we are doing subtraction, when can we when can we write them in this way? So for example, let's say I'm dealing with a problem and I have, let's say, square root of k plus square root of j minus k square root of, let's say, b now. Now, it's possible for us to be able to write k, j, and b as a product of a perfect square and another number. So let's say, for instance, k can be written as, so let's say k equals u multiplied by v squared, and let's say j can be written as u multiplied by d squared, and let's say b can be written as u multiplied by x squared. So that implies that this entire thing, I can then rewrite it here and say this is going to be square root of, so instead of k, I'm going to have u multiplied by v squared plus square root of j will be u multiplied by d squared minus k, square root of b will be what? U multiplied by x squared. Now, from what I've explained earlier, you can see that product of roots is the same thing as root of product. Therefore, I can easily write this as square root of u multiplied by square root of v squared plus square root of u multiplied by square root of d squared minus k times square root of u multiplied by square root of x squared. Now, this implies square root can easily cancel square out here. So this guy, they cancel out, and so what are you going to be left with here? You're going to have v multiplied by square root of u plus d multiplied by square root of u minus, now k and x can multiply now, multiply by square root of u. So now that you see that all of them have the same root, therefore you can factorize the u out and just have v plus d minus kx multiplied by square root of u. So that's how you deal with cases where you have addition and subtraction. They have different things under the roots, but at the same time, you can easily express them as a common root. And that's like another thing about surd. Now, for multiplication and addition of surd, I've been able to explain, and subtraction, I've been able to explain how they go. Now, but there's something about division. There's something about division of surd that is very, very important. Whenever you have a surdic expression and you have it in fraction form, so for instance, you have, let's say, something of the form a divided by root b, or you have something of the form k divided by a plus root m, or you have something of the form c divided by b plus, no, let me make it b minus root j. Now, whenever you have something of this form, what do we do? So I want to give another example. Let's say we have k divided by square root of u plus square root of v. Now, how do we do this? There's something we call rationalization. This process is the process we go through to get rid of surdic expression from denominators. And what we need to do is to get the conjugate that we use to rationalize it. So to get the conjugate, what do we need to do? We need to to rationalize, we need to get the conjugate. Now, if you notice this is a single root. So square root of b. Its conjugate is also going to be square root of b because square root of b multiplied by square root of b is going to be b. Now, if you have a plus root m, all you have to do is to change the sign. That will be a minus root m. And take note, whenever you multiply a plus root m with a minus root m, all you need to do is, you don't need to stress yourself, just square individuals. A, just square it, that will be a squared. Root m, when you square it, root m squared, the square will cancel square root and you have m. So just put minus m. This is what always happens whenever you multiply a surdic expression with their conjugate. Now, let us go further. If you have b minus root j, definitely the conjugate is going to be b plus what? Root j. And if you have square root of u plus square root of v, this is going to be what? Square root of u minus square root of v. Now, but it's a very, very important thing I want to call your attention to. If I ask you to find something and you are to rationalize a denominator which has this expression, a plus m. Now, you might be tempted to say that the conjugate of this is square root of a minus m. Then, if you do that, you will actually be very wrong because this is a single root. It is not the same thing as one of these, or one of these. These ones, the roots are separated. So this is actually the same thing as this. So the conjugate of this is just the same thing as square root of a plus n. Or technically, the agent of rationalization is just square root of a plus n. So take note of that. Whenever you have a single root, you do not need to change the sign. You do not need to change the sign. And that concludes our class for day 4, indices and surds. I'll see you in the next class.